Hi, everyone. Thank you for listening to our presentation on the satellite-based entanglement distribution over 1,200 kilometers. My name is David Schoening.
My name is John Funk.
My name is Kayla Tran.
And my name is Teresa Quach. So, quantum entanglement refers to the link between two particles in the way that if you know what one state the first particle is in, you automatically know what state the second particle is in. In this example, the first particle is red, and therefore we know that the second particle is blue, and vice versa. It's been known that entanglement has been made possible using optical fibers across a few kilometers on Earth, but due to the Earth's atmosphere and the fiber itself, photon loss is inevitable, especially across greater distances. Now, the big question is, how do we distribute these entangled particles over greater distances on Earth? One solution was to break up the entire distance into smaller segments, but even then, storage time and retrieval rates may be compromised. As a solution to this, satellites were introduced into the picture. By utilizing the vacuum of space as a form of transportation, we managed to accurately preserve the state of the photon even across 1,200 kilometers. In the big picture, this serves as a form of secure communication where information is basically being teleported via unhackable encryption keys, as well as a first step into a future global quantum network.
Regarding how the researchers addressed the main technical challenges, one of the first challenges is tracking. Both the satellite and ground stations have to be aligned perfectly for photons to be received. To solve this, they use a system called APT, acquisition, pointing, and tracking, which involve fast steering mirrors and laser beacons to lock onto the ground stations with sub-milleradian precision. Another issue was polarization drift caused by the satellite's movement. That was solved using motorized wave plates to actively correct the signal's polarization in real time. Synchronization was also crucial. They used pulse lasers to tag the photon arrivals with high time precision down to 0.77 nanoseconds to detect entangled pairs accurately.
So this experiment opens up some pretty big possibilities. One of the main things is secure communication. It makes quantum key distribution possible without needing a trusted relay. It also supports quantum teleportation over long distances, which is a big deal for future tech. And overall, it helps set the stage for building a global quantum network, kind of like the foundation for a quantum version of the internet. Regarding the key result, in the experiment, they were able to send entangled photons over 1,200 kilometers using a satellite, something that's never been done before. They saw a clear violation of Bell's inequality, which confirms the entanglement actually held up. The state fidelity was really high, around 0.87, which shows the quality was strong. And what's even more impressive is that the satellite link was up to 17 orders of magnitude more efficient than using fiber. All of this shows that long-distance quantum entanglement from space is definitely possible.
As noted throughout the presentation, the satellite was able to communicate between ground stations that were 1,200 kilometers apart. This is notable as the previous record was only 100 kilometers. With a growth of 12 times, as demonstrated by the lines on the screen, this is more than significant. The accuracy is also notable. By using the APT systems, a 0.14 milliradian accuracy was measured. This is comparable to trying to locate a dime within a 150-meter radius. While these numbers are significant, what's more noteworthy is the scientific progress that was made by this setup. What was once theory of being able to use these particles and speculation can now be used by engineers and government to change our world of communication. Potential questions that could be asked regarding this technology is why is it not used as the universal form of the internet? Why not just use fiber optic cables if the distance and accuracy of these satellites are of greater value? The main reason is cost, as in always. These satellites are expensive. They require trained physicists and people with great technical experience setting up these satellites, which cost a lot more than simple fiber optic cables. That is our presentation, and thank you for listening.